Hey, so we're going to talk about a recurrence relation for which we can't use the Master Theorem. So this has a lot of similarities to algorithm B in the first problem of homework 4. So it might be helpful for that. If you've looked at the Desmos activity, this is also the same problem that's in there. So let's imagine that we have a chessboard. Right? It has some rows, some columns. And let's say the number of squares on each side is 2 to the n. What we want to do is actually remove one square. So I'll take this square at the bottom, say, but we could remove a square anywhere. So we have this chessboard without one square. So chessboard minus one square. And what do we want to do? We want to tile with triominoes that look like this. Right? 3 squares and forming a right angle. So the question is, can we always do this, no matter what value of n we have? So let's look at the smallest possible case. Right, the smallest chessboard we could have here is 2 to the 1 by 2 to the 1. If we get rid of one square, like that, then it exactly matches the triomino. Okay, so if n equals 1, then we can do it. It turns out that we can do this for any n, and we use a divide and conquer method. So let's see how. We'll get the idea by looking at the next one up, at n equals 2, but then we would be able to prove that we could extend it. I won't do that full proof here, because it's not the focus of this video. But we want 2 to the 2 squares on each side here, so we want a 4 by 4 grid. Two to the 2. And I'm going to remove a square. I could remove any square. Let's say I remove this one. So what we're going to do is we're going to split this 2 by 2 to the 2 by 2 to the 2 square up into 4 2 to the 1 by 2 to the 1 squares. Okay, so this looks like before, right? It's a 2 to the 1 by 2 to the 1 square with one missing piece. But the others all have 4 pieces, so what do we do with them? Well, the answer is we put a triomino right here. And so now each one of these also looks like before. And so we can tile them. And for higher n, the pattern would be to put the triomino at the center to make wholes and then split into 4 smaller boards. So like I said, I'm not actually going to prove that this works, that proof is possible. Here we're going to answer a different question. Which is, how many triominoes do we need for a 2 to the n by 2 to the n board? There are multiple ways to answer this, but one of them uses our algorithm. So let's say the number we need is f of n. Now, in our algorithm, we were placing one triomino at the center and then splitting into 4 smaller boards. Okay, well, we can keep repeating this recursion relation. So this is our recurrence relation, right? Relating f of n to f of n minus 1. We can't use the Master Theorem on this because we're not dividing by anything here. We're subtracting instead. So we need a different method. So we can sort of keep this recurrence relation going, right? F of n minus 1 is 1 plus 4 f of n minus 2. So what we get here is 1 plus 4 squared times f of n minus 2, which is 1 plus 4 plus 16 plus 4 cubed, f of n minus 3. Keep going. This is going to become 1 plus 4 plus 16 plus dot 4 to the n minus 2 plus 4 to the n minus 1 times f of 1. Now, how many triominoes did we need for a 2 to the 1 by 2 to the 1 board? Well, that was just 1, so f of n equals 1. So this is the sum from I equals 0 to n minus 1 of 4 to the I. Which, if we're a little clever, or use what we know about geometric series, or sorry, sequences, we can find is 4 to the n minus 1 over 3. Right, and so the time complexity of this is 4 to the n, which is really big, much bigger than anything we would get out of cases where the Master Theorem applies. So this is how we find the time complexity of an algorithm that works like this. I hope this was helpful.